So I'm going to talk about right now trends that you find in the periodic table. Specifically, I'm going to talk about atomic size and ionization energy. And these trends that we see in the periodic table are going to help us to understand why elements act the way that they do later on in the next unit. So the first trend we are going to talk about is atomic size. Now, atomic size is the distance from the valence electrons of an element to its nucleus. So distance between the nucleus and valence electrons. Now remember, your valence electrons are the electrons in the outermost energy level. So these electrons are the ones that are the farthest out from your nucleus. Okay. And they're actually the ones that the element will either lose or gain. It'll gain more valence electrons to become an ion. So if it loses valence electrons, it becomes a cation, it becomes positively charged. If it gains electrons, it becomes an anion to become negatively charged. All right, so let's look at this trend and make sure we understand it. So I'm going to first talk about the trend down the table. Now, as you move down a group, the atomic size increases. Now, the reason why it does this, let's think and make sure that this makes sense. I'm going to draw a picture really quickly of this first energy level. So I've got my nucleus here, and for hydrogen, it's only got one valence electron, and that valence electron is in the first energy level, right here. Okay. So not that big. Now, as I move down this group from lithium to sodium to potassium to rubidium to, if I do it for any of these, moving down the group, what happens is I end up with more energy levels. So as you can see right here, as we learned how to write the electron configuration, this is going to be 5s1. So you're going to still have your spherical shape, but it's going to be much bigger than the 1s. So I'm going to draw this up here for you, just for you to get an idea. I'm going to go back to the Bohr model, showing just the orbiting, even though we know that that's not correct, just for you to see. So this is the first energy level, this is the second energy level, third, fourth, and then the fifth. Now, if I use the definition of atomic size now, and I say, okay, the atomic size is the distance between the nucleus and valence electrons. Here's the nucleus for hydrogen, and here is its valence electron. It would be this distance right here. For rubidium, its valence electrons are in the fifth energy level. Its nucleus is here, so it's that entire distance. So this is obviously larger than hydrogen. So as you move down the group, as it says right here, the atomic size increases. Now, as I go across a specific period, or I go across a row, what happens, the trend, this doesn't always happen because as you notice from your drawing, the transition metals don't actually have as severe of an increase, okay? But what tends to happen as you move across a period is that the atomic size decreases. Now let's think about why. I'm going to use group 2 right here. So I start with lithium, beryllium, and I go all the way across. Now, if you think about this, yes, I agree, you're adding electrons. So here you've got 2s1, 2s2. Here, these guys, boron would have 2s2, 2p1. So I'll write here 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So yes, you are adding electrons. So you would think, since electrons would repel one another because they are both negatively charged, you would expect for the size, the atomic size, to increase. However, what's also happening as you move across a row is that the number of protons also increases. So the increase in number of protons as you become more and more and more positive, you got 3 here, 4 here, 5, 6, 7, 8, 9, 10, that overwhelms the increase in electrons. So you're increasing your number of protons, and remember, protons, because they are positively charged, they will attract the electrons. And so they are literally gonna, so here's your nucleus, they're gonna pull the electrons in more and more as this becomes more and more and more positive, causing the size, the atomic size, which is the distance between the nucleus and the valence electrons, to decrease. So as you move across the table, your atomic size decreases. As you move down the table, the atomic size increases. Now, we've got one other trend to go over, and that is ionization energy. So I'm first going to start with a definition of ionization energy. Okay. So, your ionization energy is the energy required to remove one electron from an atom. Remember, ion meaning a positive or negative charge, having a charge. So your ionization energy is the energy required to remove an electron. All right, so if you think about it, we're going to relate right now the atomic size and the ionization energy. So if you think about it, if I've got, I'm going to draw one atom right here. It's going to be really small with an electron right here. And then I'm going to draw another one with a bunch of energy levels. Okay. Now I want to compare the energy required to remove this electron right here versus this electron out here. Okay. Because this electron is so close to the nucleus, which is positively charged, this attraction is going to be a lot stronger than this attraction here because this electron is quite a bit farther away from the nucleus. So, if this attraction is very large, so it has a high attraction, what that tells me is that it's going to require more energy to remove this electron than to remove this electron, because this nucleus is holding on tight to this electron. I'm going to have to put in more energy to remove this one than to remove this one. So this has high ionization energy. I'm just going to write IE. All right. Well, this one has a low ionization energy. Now, let's relate ionization energy now and atomic size. So, if you have something that looks like this and it has a high ionization energy, well, that's because it has a low atomic size. All right? Here, this has a low ionization energy because it has a large atomic size. So looking at this relationship, when atomic size is low, ionization energy is high, you can deduce that ionization energy and atomic size are inversely related. So I'm going to go back right now. Let's go back to this periodic table. Okay. And let's plug in here the trend for ionization energy. So as you move down a group, your atomic size increases. When your atomic size increases, that means your ionization energy decreases. As I move across a group, when my atomic size decreases, that means my ionization energy increases. All right? So what I want you to do right now, I'm going to do the first practice problem with you, and then you're going to complete all of these four and then all of the other four for ionization energy. Okay? And you're determining here which one has a larger atomic size, and for the other one, you're determining which has a larger ionization energy. So you'll have a total of 7 quick practice problems. So I'm going to compare right now lithium and beryllium. So if I compare, lithium's right here, beryllium's right here. So I want to know which one has a larger size, atomic size. Well, as I go across the periodic table, my atomic size decreases, which means lithium is larger. All right, what I'm actually going to do right now, I'm going to do the other practice problem with you for ionization energy, and then I'll have you complete all of the rest of them, so it's a total of 6 for homework. Now, I've got nitrogen and fluorine, and I want to compare which one has a larger ionization energy. So if I compare them right here, I put them right next to one another, what you should be able to see, you've got nitrogen right here, you've got fluorine right here. Now remember, as you go across the periodic table, your atomic size decreases, which means your ionization energy increases. So what that tells me is that fluorine will have a higher ionization energy. All right, so complete the other 6 and then you're done.